Hey folks, I'm taking this episode to advertise for other podcasts. If you enjoy stories about the people behind the technology that we use, you should check out the Greater Than Code podcast. They focus on the human side of software development with stories of diversity and inclusion, accessibility from people that you don't normally hear from. Search for Greater Than Code in your favorite podcast app or check out greaterthancode.com. Hi, this is Scott Hanselman. This is another episode of Hansel Minutes. Today I'm talking with Dr. Corey Frazier. He's an engineering manager at Intel Corporation, and you worked on the Space Shuttle. You've got the most amazing LinkedIn. I am just enjoying reading your LinkedIn, and that is not something I can say about everybody.
Thank you, Scott. I appreciate it. Thank you very much for having me on.
No, it's absolutely my pleasure. It must be pretty exciting to get to work on kind of two of the main technological improvements of the 20th and now the 21st century, the Space Shuttle and then semiconductors.
Yeah, most definitely. I can't lie. I pretty much won the lottery in that regard and working on some of the most complex technical challenges that humankind is working on. I think the Space Shuttle itself was called one of the most complex, engineering efforts at the time. And then now you have semiconductors with the level of complexity it gets to as you get smaller and smaller, and then supercomputers themselves are entire systems that have complexity, approaching, but not quite that level, but getting closer to things like aerospace or medical or something like that. So yeah, it's really, really cool.
Mm-hmm. So your undergrad is in aerospace engineering, and then your master's was in mechanical engineering with a specialization on thermal and fluid sciences. And then you got a PhD in mechanical engineering. Is mechanical engineering it's a pretty big, wide open field? Do you have a specialization within mechanical engineering?
Yeah, I would say my specialization from like a master's level was, more the shock waves, looking at heat transfer, particularly heat transfer in these shock tube test apparatuses at long test times, which we use to characterize chemical reactions over a certain period of time to see what the derivative chemical reactions are. And then as I got to my doctorate, my specialization was on the combustion side of solid rocket propellants, specifically the modeling of them with nanocatalytic additives.
Mm-hmm. So I've got your thesis open here, and I read it to the best of my community college degree. And one of the things that struck me is that you're exploring how ammonium perchlorate behaves. And is the goal here to make it burn hotter and faster and increase the rate that it burns so that it has more explosiveness and then takes the space shuttle up faster?
Yeah. And for the Space Shuttle program, they have their special blend, which it's fairly standard with ammonium perchlorate and iron oxides and a little bit of aluminum to help taint it, and then their fuel. But in the case of what we were studying in that research is used a lot for things like maybe missile research. Where you have certain rockets or some sort of propelled body with a solid propellant, and you're trying to get to perform in certain regimes where maybe it has a very high burn rate, like really fast, like you were saying, but you can get maybe to a target faster or something of that nature. Or sometimes you may want to see what the effect of a nano additive could be, some metal oxide to maybe make it burn longer over a longer period of time or maybe slower. And then there's other regimes that get very interesting, like mesa burning, where maybe it'll burn really fast and hot and then kind of flatten out in this burn rate and then maybe decrease. Or an intermittent situation where it burns hot and fast and then suddenly kind of stops for a second because of maybe some of the way the geometry is changing, or some of the way the fluid properties are working on the propellant as it's actually burning. And so it kind of stops for a second and then starts again. So these are all different things that the military uses for whatever application they may be using it for, which I would not know, but they find it interesting.
Indeed. Well, I think we've all, been at a cookout or at a campfire, and we've burned wood and then sprayed it with something we shouldn't have sprayed it with, like an
Hmm.
accelerant to go and make the barbecue go faster. But mostly that just kind of makes the fire go
Hmm.
flump, and then we go, "Wow, that was interesting." But you're describing not just how things burn, but how they burn over time with. And I assume the goal is to be able to have control, right? You don't want to just light something on fire and then just hope for the best.
Exactly. You pretty much nailed it in a much simpler explanation than I was providing earlier. It's they're looking for a way to control the burn rate, because the thing about a solid propellant versus a liquid one, like you were just describing, on a
Hmm.
fire and you squirt, gasoline or something on it. That's control. You throttle that by, how much you're squeezing and pressing or whatever the case may be, right?
Hmm.
Much like the space shuttle's external tank with the liquid propellant that comes through. But a solid propellant, once you light that, it's pretty much going. You can't really
Mm-hmm.
stop it until it pretty much burns out. And so the idea is, how do we control the burn rate of a solid propellant in a rocket, but at the same time have do so with just whatever the propellant itself is, or the properties, or the design and shape of the motor itself, without having to actually introduce any other mechanisms to try to, funky motor designs or something like that to control the burning rate, or some unique device.
Hmm. Is solid propellant in a rocket solid because we want it to be very dense and have more, like, the amount of space that it occupies versus the amount of potential power that it represents? Or why is it solid? Why isn't it just liquid?
Yeah. Well, there's multiple reasons. There's uh, what you can pack into it, the density, like you were saying,
Hmm.
but there's also shelf life. So when you have a solid
Mm-hmm.
propellant, in fact, a good example is your airbags in your car, right? How it deploys quickly and fast. When an accident happens and the little igniter, um, goes off, that causes
Hmm.
the propellant to burn very fast, and then fill up
Right.
the airbag with all the expunged gases. Um,
Hmm.
that ability to store that propellant somewhere on the
Hmm.
shelf for years at a time, and then have it still work, is part of the benefit.
Oh my goodness. How do people practice this though? If you've got something that's burning at, I don't know, 1400 Kelvin, how do you experiment with this? And how are the people who did the experiments not all dead?
This great question. Uh, Very carefully. It's amazing. Even as a college student, you're going through alcohol, tobacco, and firearms training. About how to handle this stuff, right?
Really?
Yeah, in fact, there's sidebar. Whenever you get a chance, maybe Google the Pepco disaster. But Pepco was a place. It was a chemical plant that had ammonium perchlorate stored within its various storage areas, and it didn't do a good job of keeping it clean. And so there was like particulate dust of
Hmm.
ammonium perchlorate around. Plus, they had lots of canisters and containers underneath a lot of pressure,
Hmm.
and ammonium perchlorate.
That was in 1998. And the thing that
Yeah,
was interesting
yeah,
about it was that it was one of only two places in America that would produce ammonium perchlorate.
right.
And you'd think that if they're making it, they would know how not to break it. And in fact, two people died, and it cost almost $200 million in property damage. Horrible, horrible thing.
Yeah, yeah. Wow, yeah. You recall way more about it than I
I
did.
try, I try to do my research when I have PhDs on the show.
Yeah, and it was just amazing because I won't say they forgot. 'Cause I'm sure they didn't forget
Indeed.
this, but there was probably a degree of, I don't know, vigilance and safety that
Mm.
maybe just wasn't followed. But ammonium perchlorate, it's really its own fuel and
Hmm.
oxidizer, and under high enough pressures, it experiences enough temperature such that it could start to undergo, this gasification that will lead to a combustion event.
Hmm.
And so going back to, us now as students, we have the ammonium perchlorate. We actually had to wear like lab coats and EMI or EMI. electromagnetic discharge, static discharge. I can't remember. It's not EMI. It's another acronym that's escaping me right now.
Mm-hmm.
But we had to wear special shoes, which were made by Converse, I believe, if I recall. So that was actually kind of cool. We got to wear Converse sneakers that were for like being in the lab.
Wow.
Uh, but we had to wear these special shoes to make sure we didn't have any electrical discharge that would happen and possibly, make the ammonium perchlorate go off. We actually had the lab when it was constructed, and this is at Texas A&M at the Turbo Machinery Lab, just to
Mm-hmm.
give them a bit of a shout. We actually had to construct the lab, and we had to build in steel, rebar, and we actually had a test cell so that all the diagnostic, work that happened on the computer, taking in the data from the rise in pressure and temperature when we had the propellant within what we call a strand bomb. Um, all of that was behind these reinforced walls, such that if something did happen, it
Mm-hmm.
wouldn't endanger us.
Oh my goodness.
Yeah, so it was pretty nuts, and it was funny. We actually had shock tube testing going on next door, where we were doing other chemical kinetics experiments.
Mm-hmm.
So it was like, there was a lot of reinforcement going on. But
Yeah.
yeah, it's a lot of safety protocols, a lot of making sure that you're not carrying things forward and back and that you have no static charge on your body. In some ways, often we probably viewed it as overkill a little bit, but, it, the smallest thing could happen. And when that happens, then you look back on it and, say, okay, take every precaution we need to.
Yeah. Safety first. Those
Yeah.
those shoes are ESD shoes,
ESD.
electrostatic
There we
dissipative
go.
shoes. Yeah, those are no joke. It's not just your regular old shoes. You got to make
Right.
sure that they have to let that electricity go into the ground, right? You're basically grounding yourself.
Yep, exactly. In fact, you had a little tag and you stick the tag. Actually, Intel is kind of the same thing for the folks who
Mm-hmm.
go and, and test the different, the quality of the silicon and everything and run it through its validation.
Now, you made a comment a few paragraphs ago where you said that this ammonium perchlorate is its own it's a fuel and an oxidizer,
Mm-hmm,
but then your PhD thesis talks about these additives, these nano additives. So I
mm-hmm.
know nano means small.
Yeah.
What kind of small things are we adding that's going to make it better than it already is?
Yeah. So at the time, I'm not sure where the research is now, but at the
Mm.
time we were adding metal oxides. So things like ceria or titania or titanium oxide.
Oh wow, like tiny
Yeah,
pieces of metal?
exactly. Yeah, and bonded with oxygen. And basically, these tiny pieces of metal, the smaller and smaller you can get,
Mm-hmm.
it creates more of a reaction site because you've increased the surface area upon which different chemical reactions can occur.
Oh.
Yeah, so that's the idea of using these metal oxides. The metal piece, and this is probably going a little bit super in depth into
Mm-hmm.
a level of chemistry that I don't have, but the metals probably have some sort of electron level
Mm-hmm.
behavior that helps stimulate chemical reactions more effectively especially when combined with the
Mm-hmm.
oxygen. But the size of these particles are what enable them to be effective because one, you're able to get more into the chemical composition of the solid propellant, but then you've got so many of them around,
Mm.
it winds up creating more reaction sites. Just like almost, well, yeah, because like I was saying before, you increased your surface area,
Mm-hmm.
so now you've got more space available upon which to actually have a chemical reaction, which helps stimulate the burn rate, the combustion reaction of the propellant.
Hey, friends, you know how I love great podcasts, and I want you to check out the Code Newbie podcast. It's all about stories from folks on their coding journey. They talk to new developers, experienced developers, and everyone in between about how they got started learning to code, how they navigate their technical careers, and they also do deep dives into technical topics in a newbie-friendly way. Check out their podcast at www.codenewbie, that's NEWBIE.org/podcast. That's codenewbie.org/podcast. So you bring up a really interesting question. So for those of us that are like regular people, we kind of mythologize PhDs. Like it's such an amazing thing that you have such a deep specialization in a thing. But that you just, for example, said, well, that goes farther into chemistry than your PhD goes.
Mhm.
When that's kind of cool. Like I just assume y'all know everything. but you're saying that there's a specialization. Do you then work side
Yeah.
by side with like with a chemistry PhD, and then they reach their limit, and then they find a material sciences PhD, and then you all work together?
That's pretty much it. In fact, when I was doing my research, there was a material scientist over at University of Central Florida that we were working with, and he was able to look at what we call the agglomeration, and basically that's when you're creating these nanoparticles.
Mm-hmm.
Like anything in nature, whether it's, I don't know, rocks in space, they're trying to come together to form planets or something
Mm-hmm.
else. When you're trying to make something super small, it'll want to have a desire to come together with other things, right? And make it a little
Mm.
bit bigger. But you don't want that because the larger size you get, the less reaction sites you have. So with his material science background, he was able to put these nanoparticles through the various processes to actually make them small enough so they wouldn't agglomerate or come back together.
Mm-hmm.
And so it was his expertise and his know-how as a chemist and wherever the
Mm.
machines and the processes that he was using to actually create these particles at as fine a size as we were looking for.
Mm-hmm. So let me shift the conversation, because you and I met when we were volunteering to teach young people
Mm-hmm.
science, technology, and math. And I'm looking here in your PhD, and I'm looking at some of your energy equations. And
Okay.
I'm teaching my 11-year-old algebra now, and he's getting into quadratic equations and stuff
Mm-hmm.
like that. And I'm trying to understand, how do we take an 11-year-old or a 13-year-old or a 15-year-old and in just 10 years turn them into a PhD candidate?
Mm.
How does that happen? How do we make
Yeah.
more Corey Fraziers?
Yeah.
And how do we scale that? I mean, were
Yeah.
you doing advanced math when you were 10 and you had a jump start? Or was it sponsorship and mentorship? What took you that far?
Yeah, that's a great question. And I think you touched on something that I think is really important for me to say that hopefully will demystify maybe the whole being a PhD thing, and that's that I actually don't like math that much. Yeah,
Oh my God, this interview is over.
right.
It's done. I'm hitting
Yeah,
stop.
I'm a heretic. Um, but honestly, beyond algebra, I'm not really a fan of math. But yet you have to take one at each new graduate degree
Mm.
level. You have to make it through that
Hmm.
class, and I will be honest, I made it through those classes by the skin of my teeth. Um,
Mm.
but the thing is, I think that shows that being a PhD is there is no cut formula. There is no template, no expectation that every PhD has all of these skill sets that you would expect. So not every PhD is great at math, or
Mm.
enjoys it. Not every PhD enjoys, I don't know, chemical equations and balancing those equations, right?
Mm.
But the PhD as a uh, the, uh, the nomenclature of it and the idea behind it is that you understand enough of the principles that you can go and better understand something through investigation, through research, through deeper
Mm.
diving. So you can teach yourself or come up with those scientific understandings by virtue of employing whatever the methods and principles are that you learned. And so, to
Right.
the point that you were making about, you know, uh, getting your son started on math, and certainly I had no far more advanced level of math than anybody else. But the idea is to get kids interested, you got to get them started early. That doesn't mean that
Right.
later isn't a good thing to do, but the earlier you get a child to see themselves doing math, doing science,
Mm.
and interacting with people who they know, can do this, or who or look
Hmm.
like them, or who sound like them, or who have the same interests. Um,
Hmm.
the more likely they are to pursue these careers, and the more likely that they're going to be resilient against obstacles in these careers, because
Mm.
some of the biggest
Right.
challenges are for kids isn't that they don't like math and science and so they don't go into it. Is that they start to see things as a challenge from the standpoint of, okay, these problems were hard, in this class in science or in math. I don't want to deal with that, or I feel embarrassed that these other kids over here were able to understand, this problem and I wasn't. So I need to now retreat from that.
Hmm.
Or, maybe it doesn't seem as cool anymore. Maybe there's a societal pressure for them to back away from being smart. I think it's a little bit less apparent nowadays because nerds kind of rule the world a little bit more than they used to. When you
Yeah,
and
the
I,
nerds will inherit the earth, right?
right, um, but I think the more you tie in their ability to do these things and seeing other people
Mm.
who maybe they identify with or maybe they even admire who are able to go down this path, it's even better.
Yeah, and to your credit, one of the things that is a characteristic that you're known for, and I'm going to use one of your LinkedIn recommendations as an example, is conscientiousness, meticulousness, and thoughtfulness. You don't necessarily have to be an expert at everything
Right.
if you have attention to detail.
Hmm.
My son or my theoretical daughter doesn't have to love math, but they have to respect it, know that it's a tool,
Exactly.
and double check their work is what the current
Hmm.
thing the 11-year-old is working on right now. Is like, you don't have to love it, but if you double check it, it's a tool, and it's a very powerful
Hmm.
tool.
And to be honest, that meticulousness and that approach, I think will not only benefit yourself, but benefits anybody. And I say this all the time about, STEM or STEAM is that even if you don't go into a traditional science or technology or mathematics based field and you pursue something
Hmm.
that's more on the art side, having technical knowledge will help you in your art. Having an understanding of being detail oriented, double checking, understanding, seeing
Mm.
things through a method, through an algorithm, in your head will make it far easier for you to take those things and execute those steps in your art. And honestly,
Mm.
it helps me a lot, not even just with engineering or something technical or, excuse me, or super technical,
Hmm.
but spreadsheets. When I'm working on spreadsheets and I'm doing something that's a high pressure situation for some executive, or trying to crunch
Hmm.
out some document or some kind, often my
Hmm.
ability to double check something or see the algorithm for how it needs to be executed saves me time or makes me look really good in front of that executive person because I'm able to execute to some kind of method.
Hmm. The thing that I want them to understand also is that there's so much power in this. Like you were talking about blowing things up, but what you're actually talking about is
Mm,
theorizing that things will work a certain
hmm.
kind of way, then testing it and proving that you do in fact have an understanding. Like these models, these
Hmm.
equations, for lack of a better word, they've been proven to be factual because we observed that they are in fact what they say they are. Like you are predicting the future
Yeah.
with math and then proving it by doing actual
Hmm.
experiments.
Exactly. To be honest, that's the thing that interested me, excuse me, the most about working with models and simulations, and why I was so keen to do this project work when my advisor approached me about it is because at the end of the day, prediction is about helping people see around corners. And when I started to reframe everything, because I was helping my lab mates
Mm.
see around the corners of what tests, what chemical compositions should we execute or should we go and develop and then, test our theories on. So that way we save time, we save energy, we save resources.
Hmm.
And I take that same application to engineers at Intel, where we do thermal and structural analysis for, supercomputing hardware. And I tell them that, hey, the reason we're doing this prediction is not for the sake of data and just feeling gee whiz about getting temperature and all these numbers coming up all over the place. It's so we can help people make decisions more effectively earlier to save cost and bring about a better experience.
Hmm. Yeah, and I suppose if you got the model wrong, you could waste a year building a whole real thing and say, "Oh, we
Yep.
were off by an order of magnitude. We missed a zero there. You got to tear it all down, start over."
Yeah, that is entirely possible. Hopefully, when you have a model, you can put it
Mm.
through enough tests or put it through the paces just enough so that you can catch, a mathematical error or some other semantic issue, that won't affect the end product, right? Yeah.
Hmm. Now you were working while you were getting your doctorate, so you were basically commuting. Were you working at night and doing your doctorate in the day, or how many hours did you have extra hours we didn't know about?
The answer is yes to both. But yeah, I was actually working full time in the space program, and then driving 2 hours one way from Southeast Houston and all the way up to College Station to go to Texas A&M, and do making that commute anywhere from 1 to 3 times a week for about 3 years.
Oh my
And
God.
yeah, it was a very interesting experience. But what I did was basically you hit it on the head. Sometimes I was working during the day, and then I would go to school in the day, and then somewhat at night. And then sometimes I would wind up working at night or on the weekends. Fortunately, my job was very charitable, and they were willing to support me. I mean, the team I had at my job was willing to support me, and I would pick up the slack for them when it came to work and things like that. So I was working both day
Mm.
and night.
Oh my goodness. I was working 9 to 5 and going to school 6 to 10.
Oh,
Although
wow.
it took me 11 years to finish my undergraduate. So I can relate. I can't relate to the 2 hour commute. My commute was only 45 minutes. But what are you doing in that? You listening to books on tape? What are you doing? Because that's wasted time if you're not filling your brain up.
Exactly. I would say those 3 years were the years where I really fell in love with audiobooks.
Mm.
That's all I did was listen to audiobooks and NPR for two
Yeah.
hours.
Yeah, I drive up to Microsoft from Portland. It's 4 hours up and
Yeah.
about 7 hours down. And audiobooks and NPR and the occasional conference call are definitely the way
Hmm.
to do it.
Hmm.
So now I met you at iUrban Teen, where we were both giving talks on getting kids excited about STEM. Other than telling your story, how do you shake these children and say, look at what you can do if you just stick your mind to it, if you just keep the faith and do that commute? How do you get kids to see that this is possible?
Yeah, one of the things I'm always telling kids is like, man, you guys live in, obviously there are challenges in society, but you live in like the most amazing time ever. Like anything you want to do is at your fingertips.
They're living in the future.
Yeah, you guys almost don't have to have imagination anymore because you can just make it seem like it's actually there, whatever it is.
Mm.
Whether it's really good CGI or it's augmented reality or virtual or something else. You could pretty much say, I want to do this or I want to see it, and it can happen. And I think one of the things that's really exciting for a kid is just using the fact that there's so much accessibility. So if kids have ideas for like apps or businesses or whatever the case may be, get them started on it. Go ahead and say, hey, here you go. And a lot of this stuff, or a lot of opportunities to do these things are pretty low bar. I won't say free necessarily, but the bar is pretty low to be able to access a lot of these things.
Yeah, just the existence of Khan Academy has been extraordinary for my kids.
Yeah, exactly.
Like, how did we learn math before? I guess we had paper and we had a TI 89 calculator was basically all we had.
Yeah, yeah, and it's like, man, I wish I had so many more of these things as a kid because I would have certainly been able to have applied what the teacher was telling me,
Mm.
much more readily, and then be able to find my passions, get jump started a lot quicker rather than existing in my own head until I got to college for the most part, as far as what I wanted to do. And so I think for the most part that kids need to be able to put their hands, literally or figuratively, on the thing that we're talking about when it comes to STEM. So at iUrban Teen, we're doing at these summits, we're doing these different tests are like in the healthcare arena. If we're talking about preventative healthcare, we're talking about how we're using data analysis or AI or something to help us do better healthcare. We have actual healthcare professionals running a workshop that's showing them how this is being
Hmm.
used, right? And I think kids need to actually see that. If it's something regarding technology and everybody likes sneakers and a sneakerhead, I'm trying to become one. I'm not
Hmm.
one, but I'm trying. But if they see how, what does Nike do? I believe Matthew Nurse was up there talking about what Nike's doing with technology when he gave his talk. But if they could see how
Hmm.
technology is playing a role in the very things that they like, then that's what, gives them that sense of, okay, yeah, this is great. This is something I should pursue, because there's other things to do when it comes to Nike other than being an athlete. There's plenty of things on the technology side. There's other things I can do in sports.
Right.
In fact, sports is very much so dominated by data and technology right now, and whether it's statisticians or it's actual human performance data, right? So it's give them the opportunity to see things.
I'm hearing applied. Like it's like theoretical science is not going to lie to
There we
9-year-old
go.
up or 11-year-old. But if you tell them, like Matthew Norris, the example you gave, he's the director of the Nike Sport Research Lab. This is somebody who's taking math and science and applying it to making shoes, to making, and then ultimately making
Exactly.
athletes successful. So you got to draw a
Exactly.
straight line between that equation that my 11-year is working on and then someone's success.
Exactly. Application. We live in a world where, at this point, everybody has this immediate gratification sense. So if you're getting someone that immediate contact, an immediate touch point, it's sticking a lot more readily.
Fantastic. Well, I really appreciate you chatting with me today, Dr. Corey Frazier, and I appreciate you going out there and fostering a culture of innovation at Intel and the work you did in the space shuttle.
Oh, well, thank you very much, Scott. I really appreciate you having me on, and this has been fun. I really enjoyed it.
All right. Thank you, sir. I hopefully see you again. This has been another episode of Hansel Minutes, and we'll see you again next week.